There's a secret language that runs our entire world. It's not ancient, it's not spoken by spies, it's the language of measurement. This is the invisible set of rules that lets us build everything from the phone in your hand to the rockets that are heading to Mars. But to really get why this language is so important, you first have to understand the complete chaos that came before it. I mean, just think about it for a second. Imagine you're trying to build a skyscraper, right? A huge, magnificent building. But the measurement you're using for a foot is literally the size of your foot, and the person you're working with is using their foot. It'd be an absolute disaster, wouldn't it? Nothing would line up. The whole project would be impossible. Well, believe it or not, that's pretty much the problem we had for centuries. And this wasn't just some hypothetical problem. For most of history, measurement was a world of total confusion. Different countries, sometimes even different towns right next to each other, had their own special ways of measuring things. It made sharing scientific ideas, or even just trading goods, incredibly difficult. At the center of all this confusion were two major systems battling it out. On one side, you had the CGS system, which used the centimeter, gram, and second. And on the other, you had the FPS, or the British system, with its foot, pound, and second. Trying to translate between these two, it was a recipe for mistakes and a huge headache for anyone trying to work on a global scale. So, to clean up this global mess, the world's scientists realized they needed to do something big. They needed a single, universal language, a system so clear and so consistent that any scientist, anywhere on the planet, could use it and get the exact same results. And that solution is the Système International d'Unités, which is just the fancy French way of saying the International System of Units. We all know it as the SI system. It was officially established back in 1971, and it became the language for science, for industry, for everything. Now, just like any language, the SI system has an alphabet. These are the 7 base units, the building blocks that almost every other measurement is made from. You've got the meter for length, the kilogram for mass, the second for time, and 4 others. These 7 words are the absolute foundation of all modern science. And if you want to understand just how precise this system is, take a look at this number. So what is it? Well, that is the number of tiny energy jumps. Think of them like ticks on a tiny atomic clock that a single cesium-133 atom makes in 1 single second. Our entire definition of time is based on something that is constant throughout the universe, making it unbelievably accurate. Okay, so we've got our alphabet, those 7 base units. But in any language, just knowing the words isn't enough, right? You have to know how to speak them with the right amount of detail, with precision. So check this out. On the left, a measurement says about 4.7 meters. On the right, it says 4.700 meters. Now, why on earth would a scientist bother writing those 2 extra zeros? Are they just trying to be difficult? No. Those zeros are actually communicating something incredibly important about how the measurement was made. This is where the whole idea of significant figures comes in. The official definition sounds a little complicated, but here's the simple version. Sig Figs are how scientists tell you exactly how good their measuring tool was. The more significant figures, the more precise the tool, and the more confidence they have in that measurement. And of course, there are a few rules for counting them, but they're not too bad. You always count numbers that aren't 0, and you count any zeros that are squished between other numbers. You ignore zeros at the front, but here's the big one, the crucial one. You only count zeros at the very end of a number if you see a decimal. That little dot is a signal. It's the difference between saying roughly 4,700 and exactly 4,700. So now we've got our words, the SI units. We know how to speak them precisely using significant figures. The final piece of this whole puzzle is grammar. We need rules to make sure our scientific sentences, our equations, actually make sense. This grammar check has a name, dimensional analysis. And the main rule is something you already know. You can't add apples and oranges. It's the same idea. You can only add or subtract things that have the same basic dimension. You can't add a length to a time or take a temperature away from a mass. It just doesn't make any sense. So let's put this grammar check to the test with a classic physics equation. Now, this might look a little intimidating, but don't worry about what all the symbols mean just yet. We're just going to ask a simple question. Does this sentence make sense? Is it grammatically correct? Let's go through it piece by piece. On the left side, x is just a distance, so its dimension is length, which we write as L. Easy enough. Now on the right side. The first term is also a distance, so that's also L. Great. The next term is velocity, which is length divided by time multiplied by time. So the time on the bottom cancels with the time on the top, and we're just left with length. And the last one, acceleration, is length divided by time squared. But we multiply it by time squared. So again, they cancel out, leaving us with length. Every single term in this equation boils down to the dimension of length. It's grammatically perfect. And this all leads to a really powerful rule in science, summed up perfectly by this quote. If an equation doesn't pass this dimensional test, if the grammar is wrong, then the equation itself must be wrong. It's the very first thing a physicist does to see if a new idea is even worth looking at. So when you put all of this together, the universal words, the rules for precision, the grammar checks, you start to realize that this is way more than just a measurement system. It's a code. It's the fundamental logic that all of modern science and engineering is built on. So here's what to remember. The SI system gives us a universal alphabet that we can all agree on. Significant figures tell us how to say our words with the right amount of precision, and dimensional analysis is the grammar that makes sure our scientific sentences are logical and actually mean something. This language isn't just for physicists. It's the hidden logic, the operating system, that allows us to build the world we live in. It's why our phones work, why our bridges don't fall down, why our medicine is safe. So the real question is, now that you understand the language, what are we going to build with it next?